Hi. Welcome back. So I've realized that an hour-long video is quite a lot to ask people to watch. So what I'm going to do is I'm going to split that video up into 3 parts, maybe 4, probably just 3. And we're going to go through each of the different aspects of the two-fluid equilibrium and how this satisfies them, because this is MHD. Trying to act like it's not, or trying to say like, you've chosen some equations. That's right, I've chosen the Z-pinch equilibrium, because that's what this is. It's a pure axial flow. It's actually symmetric. That's a Z-pinch. All right? It's just disingenuous. And it's emperor's clothes situation. All right? So what we're going to do in this video really fast, because short content is better for YouTube, is we're going to cover continuity. All right? So the important thing about continuity is we have this UZ of R, and that's what makes up the flow, which is just the electron speed subtracted from the ion speed. We also have quasi-neutrality. So that's the ion velocity is equal to the electron velocity. We have a collisionless hydrogen plasma, okay, which makes things very nice to deal with, especially when we get to momentum. So what's continuity in the two-fluid model? And again, the other thing about this is that this is equal to a uniform density. All right, well, continuity is just saying we are bookkeeping. We are bookkeeping where all of our particles are going, right? If they leave the volume, we have to, as a flux, then what's going to happen is we're going to have what the amount inside decrease. That's all continuity is saying. And this is very simple. This is very simple to prove that this is satisfied for a Z-pinch, an axisymmetric Z-pinch. Because, first of all, we've got a uniform density here. And I actually have colored markers now, which is very nice. I love colored markers. Okay, so because we have a uniform density, this term goes to 0, and so does this term. The time derivatives, they go to 0 for the density, the Eulerian components. Right? I refer to those as unsteady effects. So I'm just going to go ahead and erase this. That goes away. So now the question is, do we have the divergence of the flux, the density flux, equal to 0? And the answer is yes, we do. So notice, these are uniform. Pull this one out, pull that one out. All right? What's left? What's left is the divergence of UI and the divergence of UE. And these are both the same. They're equal to n naught. So if we subtract this equation from that equation, right? So we're going to subtract 2 from 1. So we have n naught divergence of UI minus UE, which equals n naught divergence of U. And the question is, does this equal 0? Well, this amounts to the question, does divergence of U equal 0? That's the question here. Is the divergence of U equal to 0? What is the divergence of U? Well, in cylindrical coordinates, I don't have a plasma formulary with me, so bear with me. I'm going to go grab the plasma formulary. I should have had that before I came in here. Oh well. does the divergence of u go to 0? What is the divergence of u? Let's just write it out. All right? This equals 1 over r. I'm going to leave the partial derivatives here. Does this equal 0? Well, obviously it does. That's very simple to see. It's very simple to see because we have no axial gradients. That's equal to 0. We have no swirl, so that's equal to 0. And we have no radial flow. So all these things are equal to 0. Yes, divergence of u equals 0. That means that continuity is satisfied. Thank you for watching. Please make sure to like and subscribe. And please, if you have the money, consider donating to my Ko-fi. I really need it. What we're going to do next time is we're going to go through the momentum equation in the next video. And then after that, the energy equation. And then we'll finish up with Maxwell's equations. Thank you for watching.